Is this fine now?
Yes.
Yes, certainly.
Okay, okay. Yeah, sorry for the glitch because I just use this NPTEL systems here, so I'm kind of getting used to it. So yeah, now I guess the slides are moving.
Yes, sir.
Yes.
Certainly.
Yes,
Yes, sir.
Yes.
Okay, okay, fine. Thank you. Thanks for pointing it out. So yeah, we'll just get back to the discussion of trying to bring a context in localization. So if you see on the top left hand side, right, so we see the picture of a city block, right, which is sometimes we want to know in which part of the city block did a phone call originate, right, or in which part of the city you are approximately in, right. So in those cases we are often find like our application just is enabled, right, if we have a location accuracy or a granularity within like 100-meter scale, right. So every 100 meter I probably am interested in knowing whether you are in this part or this block of the city, right. But the context, as the context changes or the application changes, right, we have more and more uh, uh, inputs where the granularity or the accuracy of the system that is expected could be way much more sophisticated, right. So in case of the lower picture, right, where we have this city intersection block, the road blocks are intersecting, we are kind of interested in knowing which side of the road you are in, right, so that the GPS system sort of is accurate enough to understand, right, which road you are going to cross or what is the corresponding signal that you are facing, right. So based on the requirement that you are seeing, right, so the granularity that is required, right, whether it is every 10 meters or every 100 meters, that keeps on changing, right. And also it has some kind of tolerable accuracy, right. So even if my technology supports a granularity of 10 meters, it might not be that you are always accurate within that. So it could be uh, the accuracy can also change, right. So what we are kind of saying here is that the granularity should also contain the kind of accuracy that is required, right. I should not be like way off, I should not be inaccurate by 20 or 30 meters, right. So the granularity here also brings in the context of accuracy that is expected in such systems, right. And now if we move on to the right hand side of the slide, you see for example in a shopping mall, I am interested in knowing let's say which floor a particular person is in, so that he can get more contextual advertisements, right. So maybe there is a food court or there is a movie theater, and based on which floor he is in, this advertisement could be pushed, or I could know a little bit more about the footfall of people, right, where more people are flocking. So that could be one more granularity or accuracy kind of requirement, right. And if we just go a little bit more micro, right, where we are really wanting to pinpoint the location of the person, for example on the right hand side we see this shop, right, where we really need to know whether a person has visited a particular shop, right. So often the requirement would be sub 5 meter, okay, and all the way to where I need to know where is the customer is really looking at, or what kind of uh, merchandise is the customer interested in, right. So in that kind of cases, in those kind of cases where we often use the term physical analytics, right, where exactly the customer is coming and which portion of the shop or which portion of the mall the person is coming, that will require you something which is less than a meter, or like often decimeters, right. So we are really interested in pinpointing the location of the person or the customer within a shop, right. So this is one example, but there could be many other use cases where you might need a sub meter localization accuracy. And last but not the least, where we have robotic systems, they are really fine tuned to achieve localization accuracy in the order of often millimeters and centimeters, right. So uh, sometimes that could be necessary, okay. So we are primarily going to look at the general principles here, right. We are not going to look at particular technologies that are going to achieve millimeter scale accuracy or centimeter scale accuracy, right. So we are going to look at what are the principles that actually work under the hood to make such localization happen, right. And then there are technologies that are fine tuned to make it more and more accurate. Okay, so this is primarily the context in which we are going to be dedicating this particular workshop towards, right. So we'll have an entire sweep of this space. Okay. And on the left hand side, as you can easily correlate, these are the technologies that will be using outdoor localization technologies. The lower one definitely is a GPS, right. So GPS can give you, so in urban canyon areas, right, wherever you have big buildings, sometimes as you will notice shortly, that the localization accuracy can go down, but yeah, of course within 10 meters is something that could be guaranteed, right. And particularly if you are tracking, doing location tracking, often the GPS data is also fused with other kind of sensors to make it more and more accurate, right. So but roughly you can assume that it is of that ballpark, right. And 100 meters is often we just associate our phones with a certain cell tower, right, and based on the cell tower ID we would be able to figure out a rough estimate of this blob, right, where the circle is, right. So as you will see, more and more the accuracy or the granularity is better, we are shrinking the size of this circle, right. This is the circle of like an uncertainty, right. If bigger is the circle, more is the uncertainty, and this is something that you would be finding in Google Maps earlier, right. So if the certainty was not very high, this circle would be of a greater radius, right. And on the right hand side, which I call a little bit more challenging, because we do not have GPS indoors. So primarily these are cases of indoor localization, where you have to be first of all more accurate, right. It's not 10 meters within an indoor area might not make a lot of sense unless and until you are in a big airport or a big shopping mall, right. Suppose you want to have such technologies enabled in a home, right. In a home scenario, 10 meters is like really large, right. So this is a 10-meter radius, so you have to consider the circle of this uncertainty, which is really big, right. So we have to look at technologies that are going to give you meter level accuracy, like sub meter or sub 5 meter, depending on the context. So we are going to look at indoor localization technologies as well, right. So GPS and cellular ID could be very easily used if we are looking at outdoor localization technologies, and for indoors we have a host of sensing modalities that we are going to come through. Okay. So one example, like real example, right, that I would try to bring up where such sensing could be used is disasters, right. So often in such disaster scenarios, you do not have access to cell towers, right, and often such sites, right, like the people, the victims could be just trapped under some debris or they are indoors, right. So in these cases it is really required, right. I am just showing a very important use case where you can require a mix of both, right. Some of these victims or some of these troops could be just deployed outdoors, they might have access to GPS, but once they are basically searching for victims, and they could be entering some indoor location or locations as you see on the left hand side, like trapped under some debris, right. So you might not have a seamless way to locate a person, right. So in those cases you might also have to integrate such solutions with indoor location technologies, right. So what I say is like disconnected by disaster, where just because you do not have access to the location of the victims or a person, he is sort of, his life is in danger, right. And there are IoT solutions that could be employed in such cases for sensing, right. You are trying to do location sensing using IoT based systems, right. We are going to look at many use cases. I thought that this could be a very important real life use case where location tracking is of paramount importance. Okay. And there are many more use cases, as I have shown, right, where there is a lot of places here are already localization enabled, and then there are many situations, for example in the airport we do wait for our baggages to arrive, right, and often we do not have any idea that when exactly is the baggage going to arrive. There is no estimated time of arrival, and often we end up spending a lot of time in the airport lobby just waiting for our bag, right. So what if we have some kind of a tag here, right? Let's say if we just a minute. So if we have some kind of a tag, let me select the pen. Okay. So if we have some tag here that could be used for tracking the location of the bag, right, and for that we have to deploy a whole bunch of infrastructure in the airport, right. And you are all aware of this Google Nest kind of platform, or Alexa, right. These are the voice command controls that you have in our residences. This could also track location based on sound signals. Okay. So often they will pick up the location, or at least they are going to pick up where a person is, like from which direction a person is talking from, right. And since you have multiple of these devices, this Google Nest kind of devices deployed in your home, it is possible, right, to pick up which rooms you are frequenting more, or who are the people who are spending time together, right. So there is a lot of private information they can actually sniff through, not only just by recording the voice, but also trying to look at the position where the sound is originating from, right. And you have the shopping cart, right, where people could be entering shopping malls using and using such shopping carts, right, where they are taking the shopping cart in different portions of the mall. And of course you can even have a tag that is attached to such carts, and using these tags the cart could be localized, right. And you can very easily figure out which portions of the stalls, right, which stalls are of more importance, right, where do the customers visit more. Okay. And then I have already discussed about the disaster situation, right. So in a disaster situation, we could have the necessity of guiding this first responders who are entering this such locations for uh, picking up victims or saving victims, right, trying to figure where are they, and you also want to save them. And for that, even for the logistical management, right, where do you want to send the troops, right, you don't want to send the troops randomly, but you want to distribute the troops in evenly across different places, and for that you need to continuously track the location of these troops, right. So the location of the troops is also very important, right. And not only just for logistical reasons, but also it happens that they like fall victims to fires, right, themselves, right, or their heartbeat really goes high, and somebody, you have to send out some first aid to them, or try to bring them out of that location. And for that you need to know their position very clearly, right, otherwise you will not be able to reach them, right. So this ends up in many unfortunate incidents, and we lose a lot of them just because they are lost in this entire space, right, without any tracking information available. Okay. So on the other examples, right, we have extensive use of localization in warehouses. So warehouses, you have this different packages that are continuously being shipped from different parts of the warehouse to the other parts, right, based on when it has to be delivered, where it has to be delivered, and so on. So you need a very efficient way to track them, right. So location tracking in this scale is also very important. And last but not the least, there is a lot of application coming up in the next generation gaming, right. So in AR VR gaming systems, particularly in case of multiplayer gaming, you need to have an idea of the relative location of the different entities or the different persons who are in the game, right. So in order to make that more effective, you have to use modern localization technologies such that people can interact in the physical space as well as in the virtual space, right. So basically in the AR VR mapping or gaming, you the physical space is mapped to the virtual space, right. So if I come close to my friend in the physical space in the game, so that should also reflect such behavior in the virtual space. So for that we need a very efficient mechanism to know the relative location of the individual players who are playing the game, right. And not only just games, but there are other applications that could really immensely in the AR VR space, that could immensely be benefited if we bring in good localization technologies. Okay, and this entire thing, right, is sort of encompassed by the vision of industry 4.0, right. The in this technology we uh, sort of expect that everybody is connected to each other, right. The man and the machine, they are all connected and trying to collaboratively solve problems, right. And for that, one of the key ingredients that we need today is access to good localization infrastructure. So if we have a good way to track the location of different entities in real time, that could really contribute to the vision of industry 4.0. Okay, so what's the holy grail of localization? Okay, so what is the expectation from such technologies? We want centimeter level tracking, or let's say millimeter, or very accurate tracking. So centimeter is just a thing that I chose, but you can, these are the kind of key pointers, right. For a lot of entities, thousands of entities, every few milliseconds, which is basically some kind of an update rate at how often you are updating the location of those entities, and the cost is very less, few cents or few rupees, right. And the power consumption per entity is also very less, like microwatts of power, right, with zero infrastructure assistance, right. You don't want to go and deploy a lot of infrastructure in that area just to make it location enabled, right. So ideally the goal should be zero infrastructure. You should not be having and deploying lots of hardware, right. So just the tag should be enough, right. So that is the goal, right. How much we are able to reach that goal, that is a different question. And the environment where we are trying to locate such entities could be very complex. In indoor places, there are a lot of things like walls, you have furniture, right. There will be a lot of metals that are there. So it makes the environment very complex and not very favorable for most of the localization technologies to work, right. And it could span a few hundred square meters, right. So if you look at all the different aspects here, right, where like particularly things like the accuracy of the location tracking, the scale, and so on. So on the left hand side I show an IoT device, right. So this is an IoT device where I need to track the location for, and this is the location, right. And what are the different things, what are the different aspects that we need to keep in mind while sensing the location of this IoT device, right. So I'm just kind of paraphrasing this in the sentence below, right. But if you just look at the crux of it, right, there are different KPIs, right, if you can call it key performance indicators, or KPIs. Okay, so what is the precision of the system, what is the granularity, right, what is the accuracy of the system, right. Does it give me sub 5 meter accuracy, or it gives me let's say centimeter level accuracy. Okay, what's the precision, right, what is the granularity of the system, is it a centimeter scale precision that we will get, or it's a meter scale precision that we are going to get. How many IoT devices or how many entities, right, this can scale up to. Can it have 100 different devices that are tracked in simultaneously, or I can just have up to 10 devices, right. And why is this scalability important? Because this is also has an impact on the latency, right. So how frequently we are getting the localization updates, right, how so update frequency. Okay, so if we are getting or requiring our application to receive updates every few milliseconds, and at the same time we expect the scale of the system as like let's say thousands of devices, we have to figure out what exactly, what is the trade off, what is the right trade off we have to do, right. because we cannot have the best of all the different KPIs simultaneously, and that is what I have written in the following sentence, right. So this is basically a holy grail, right. It's very difficult to achieve something like this. We actually have to work out a balance in between these key performance indicators, and then what kind of technology that you are using that is going to save power. Okay. So we don't want our devices to die down just for location tracking. So we don't be wanting to consume a lot of battery power just for supporting localization, right. For you, for example, GPS chip is going to consume a lot of power, right, and there are specific reasons why. Similarly, many other devices, many other technologies, particularly where we use uh, wireless communication modality as a sensing medium to the track location, they will be transmitting some beacons, they will be receiving some messages, and in that way they are going to consume power in the radio, right. So we have to find out innovative ways in order to save power, both from the hardware level as well as from the kind of algorithms that we try to develop for implementing such localization protocols. We have to keep in mind whether we are communicating too much, right, or receiving a lot of messages and we are not getting enough time to sleep, the device to sleep. So in that way it can bump up the consumption of power. And then how much is the coverage? So that is also important. You are just covering a small room, or your infrastructure is able to scale up to a much larger geographical area, right. So in this place, when I say scalability, so scalability refers to, let's say, the number of entities, and this basically means the spatial coverage, okay, or the geographical area that I am trying to cover. Okay, so this is where you have seen many applications where we need IoT devices to be location enabled. We have seen lot of use cases and lot of places where localization of IoT devices is really necessary, and currently we are going to look at the technologies that could support that, right. And in this slide, as we are seeing, it is not just the technology comes with a lot of trade-offs, right. In what context we want to deploy this technology, right, whether it's you want to scale it up to a large extent and you probably don't care much about accuracy, maybe 10-meter accuracy is good enough, but in a smart city kind of scenario where you want to support several thousand devices, okay, or you want to just concentrate on a small indoor scenario where the coverage is less, we don't need to scale it up, right, maybe tens of devices are fine, but I want centimeter level accuracy and an update rate of a few hundred milliseconds, okay. So in those cases we have to basically adjust the right tuning knobs, right. What are the tuning knobs that I want to adjust in order to realize the particular KPIs that we want to achieve, okay. So coming to the coordinate space, right, I just now had a kind of brief introduction to what localization means, in what context localization could be used, and the different tuning knobs that you might have in order to regulate the performance of a localization system, right. With that laid out, we have a brief idea about what all these things mean, right. And now we will start from the very first thing, right, by defining the coordinate space, okay, because if you remember the very first slide, we had that estimating the location of an entity with respect to a fixed reference frame, right, or a fixed or a specific coordinate system, right. So for doing that, we need to first understand what this coordinate space means, and we need reference points, okay. So if you think of in the old days, we had these ships which are going around and there were no concept of latitudes and longitudes, right. Now it is there, they really have GPS device and they can know that which part of this coordinate space they are in. But in earlier days they actually depended on the sun, moon and the stars, right, the north star they could be looking at, and there are like several stars which they knew with the reference to those stars where they are, and in that way they would be able to know whether they are moving north or south or in a particular direction, okay. So you need reference points or some sort of an anchors, right, those are well defined points within your coordinate space. Okay, and you sort of correlate your location with respect to the reference point, and in that way you somehow know your location in the coordinate space. Okay, and we had like this old school things of navigating, where you have a physical compass, you have a sextant, you have a gyroscope. This kind of devices were used to do navigation, and at the same time being localized with respect to this reference point. So the reference point sort of tell you uh, where you are in the coordinate space, and sometimes these tools also tell you how, when you are navigating, whether you are navigating in the correct direction or not. Okay. So for localization to work, now you have understood that we need to define first a coordinate space. And even for GPS, right? So one of the things that we are going to cover first, like today, is the how GPS is one of the something which is ubiquitously available. Everybody knows about it. In every smartphone you have like use GPS technology, right? So that also depends on a fixed set of reference points or anchors or landmarks, and those reference points are the satellites you have, the GPS satellites that you have in the sky. And your entire earth, right, we have this latitude longitude system which basically gives us the coordinate space. Okay, so that is a spherical system. In our case we mentioned that in terms of degrees or radians, right, because our earth is round, it's not a flat 2D surface where we can simply use a 2D Euclidean or Cartesian space. It's a little bit more complicated than that, but mathematically all we are interested in is to find out the position of that car or position of that plane, right? What is the latitude, longitude, and what is the altitude also, right? So some XYZ in that particular coordinate space. And what are the reference points? As I told you, the reference points are the GPS satellites. Okay, and every device that has to localize itself, or a GPS receiver, will have this receiver chip, right? So this could be a GPS receiver chip, right? So what it is supposed to do, it actually receives the signals from the satellites, receives the signals from the satellites. Okay, so and then we are going to somehow we are going to see how this signals could be analyzed, and based on that analysis we are going to say that okay, I am in this latitude and this longitude, right? This is the latitude, this is the longitude, and this is my altitude. Okay, so these are the things that we need to compute, or the chip is going to compute. Okay, so that is something which is we should know first, right? Because any of the IoT device that is placed outdoors, in absence of any infrastructure, you have the GPS infrastructure available, right? So one of the easiest way is to just have a GPS chip that goes in such a device, and just have the GPS location. Okay, so as we will explore more and more later, right, any of such localization systems that are based on ranging, right, we are going to talk about what ranging means, are based on some kind of reference points, and those reference points could not just always be satellites, but there are other transmitters, like wireless transmitters could also be used as reference points in a coordinate system defined by us, right? If you remember, we talked about association to a cell tower, right? Suppose your phone is associated to a certain cell tower, okay, and based on my associations with different cell towers, let's say this is a tower 1, this is tower number 2, and this is tower number 3, right? So based on my associations with these different cell towers, and maybe other things like my signal strength that I am receiving from the cell towers, or trying to estimate the distance of my mobile phone from the cell towers, right, I could figure out my location. Okay, so this is D1, this will be D2, this will be D3. Or in case of a home environment or something like a shopping mall, where we are trying to reduce the coverage, we don't want hundreds of square meters of coverage, maybe much lesser than that, we can even use Wi-Fi access points. Wi-Fi APs could be used as reference points or anchors or landmarks in that home area. Okay. So, we can find out our relative position with individually with each one of these access points or the cell towers, and then using that information it will be possible to figure out the location of my device, right, of my smartphone or an IoT device, right, whatever has this location technology enabled, where exactly are they located. Now, given the system of or given the coordinate space, right, you have to tell me what is 0 0. Okay. So, what is 0 0 and what is the location of the these towers, right, you have to have a certain sense to that, right, otherwise this is sort of undefined. Okay. This is a relative location given your coordinate space. So, then as I told you, well, just bringing from the previous example, we have this arena. Okay. And this arena is basically this area where we will be restricting our technology to. So, that technology will be just restricted to this particular area or the coverage. So, outside this area we are not expected to have this localization system working. Okay. So, if you just deploy a Wi-Fi based localization system at your home, you are not expected to or while evaluating the performance of that system, we are just going to be very strict about the boundaries where it is supposed to work, and because the system level optimization that you will be doing is going to be restricted only to that area. Okay. So, in the previous slide I have shown you that how you can use different analytical methods where you have an estimate of the distances from the several different cell towers and so on, right. So, there would be another way, right, particularly using machine learning, where we try to get the signature of these reference points at a certain location. Okay. So, suppose your device is located at XU, YU and ZU, and you are trying to get some kind of a signature at this particular location with respect to these reference points, right. So, this signature could be different kinds of things that could be picked up from the signals that are being transmitted from these reference points. One of them could be simply a signal strength. Okay, these are all transmitters. Okay. So, they are going to transmit a certain signal, right, and maybe the signal strength that is being received at a certain area, right, at a certain location is sort of indicative or sort of unique in that entire area, right. So, more the number of reference points, bigger will be the dimensionality of your signature, and the dimensionality could be simply like signal strength 1 comma signal strength 2 comma signal strength 3, right. So, this because you have 3 reference points, you can have more, and that is going to increase the dimensionality of your signature here. Okay. And this basically is supposed to be unique in order to the localization system to work, right. Maybe in every block of size say x meters by x meters, the this feature vector, right, or this signature is going to be unique. Okay. And then once you go to the next block, right, this particular block of x by x, this is going to change. Okay. This block, right, this is going to change. So, every block should have its own signature, okay, or its own feature vector, and this could be used for classifying what portion of the arena you are in, right, because the arena is now going to be split up into several of such blocks, and just by looking at the signature I could actually figure out which part of the block you are in, and there will be some kind of a database, right, that has a mapping that maps signatures to such blocks. Okay. So, this is a block ID say 57, this is block ID say 58, this could be 62 and so on, right. So, that can immediately tell me that okay, your signature is like this. So, your block is block number 62, and I know what does 62 mean in this physical space in this arena, right. So, I can actually get to a certain with a certain level of granularity, right, with the granularity of x I know that I am in this block. Okay. So, GPS you have this system of satellites, right. So, currently whatever we discussed was like the two methodologies. We are going to come to them. So one was based on ranging from cell towers, Wi-Fi access points, as well as GPS, right? It could be GPS satellites also, and the other one was based on machine learning techniques, where we try to match signatures in a certain area. Okay, so now we will come to this concept of GPS, and how we will see just how the GPS technology works. Okay, so we have a constellation of several satellites, right? And at a certain portion of the world, it is not possible to view all the satellites simultaneously. So the system of satellites make sure that they are covering this entire earth, right? All the portions of the earth are uniformly covered, right? So from one portion we would be only able to see some of them, right? And it is open to the general public in May 2000, from 2000, and it is a scalable solution, right? And it is privacy preserving. Why? Because I have my own GPS chip receiver, like a receiver chip on my device, right? It's not going to send out this information unless and until it is programmed to do so, right? So it is going to just have the location of the device in itself, right? There is no other location information that you are actually sending out to the satellites. It's completely privacy preserving, right? You are containing the output of the chip in your device. Okay, and it's a scalable solution. You can have as many receivers as you feel like, right? Because all these satellites in the sky, what they are doing, they are simply broadcasting certain signals, right? And you can have n number of GPS receivers, and having more and more receivers does not slow down the process. So it is a scalable solution. Okay, so what happens, what are the basic principles that actually makes this GPS technology work? Okay, let us try to take a look at that. Okay, so every satellite here, what are they doing? They are transmitting a predetermined coded signal. Okay, so that signal is going to have a certain number of symbols or chips, right? And that code is going to be repeating every 1 millisecond. Okay, so what exactly is the setup? We have a satellite here, we have a receiver here. So this is the GPS receiver. Okay, and somehow we are trying to, what is the intention, what is the thing that we are trying to do here? We are trying to somehow find out the distance of the receiver from the satellite. Okay, and now we have to come up with a way to do that. Okay, and in order to do that, what the satellite does is the satellite keeps on transmitting a signal. Okay, why it is predetermined, why it is coded and all, we are going to come to that, but for now you can just assume it keeps on transmitting a signal like this. Okay, and just ignore the dot for the time being, just think it's a stream of ones and zeros that is being transmitted from space, right? The satellite keeps on transmitting this every 1 millisecond, and it is going to go through your atmosphere. It's going to take some time, right? Because the satellite is really far away from the earth's surface, and we are assuming that the GPS receiver is on the earth. Okay, is on the earth's surface, and whenever it comes, here it is, the same signal, maybe with a lower amplitude, because there will be some fading in the atmosphere, and it is going to be received by the GPS receiver. Okay, so now it has to understand primarily that how long this signal transmission took, right? Because if you know that how long did the transmission take, okay, so suppose you know that how long the transmission took, let's say this is t, right? Some t amount of t in microseconds or t nanoseconds, right? Whatever is your unit, right? So this multiplied by the speed of light is going to give you the distance, isn't it? Okay, distance, or often in the localization terminology we often call it a range. Okay, so if you know the time of flight that the signal took from the satellite to the receiver, multiply that value with the speed of light, because that is the approximately that will be the speed of the signal, when it is traveling through the atmosphere, maybe a little bit reduced because it's not vacuum completely, but approximately it will be the case. Okay, and then when the receiver and at the receiver we have the signal, it has arrived. Now what the receiver signal, yeah, what the received signal is going to do is going to compare that with a predetermined coded signal, because it's that is how the predetermined coded signal thing comes here, right? So I already know that what is going to be transmitted, which is often known as the gold code. Okay, so the gold code is basically the copy of the signal that I already know that the satellite is going to send me. Okay, and the satellite is keeping on transmitting this signal. Okay, so whenever I am receiving a copy of the received signal, like receiving the signal in my device, I can always try to see how the gold code matches with the received signal in terms of offset, right? I'm expecting an exact copy of the signal, but that exact copy will be delayed by some amount of time, and that time is basically the offset that I am interested in computing, right? So if you know this portion of the, as I've shown in the slide, this portion of the gold code is actually corresponding to this portion of the signal, right, the received signal. So in that way I can do this alignment, right? This alignment is necessary, right? Whatever you normally use tools like autocorrelation, right? You try to figure out how much this two time series matches with each other. So in this case also we have a very similar problem. We know what is the standard coded signal, what is the gold code, and we know where is the received signal, we know their exact bits, right? All we try to do is that how quickly or how delayed the received signal was, right? Because this is basically a delayed copy. Okay, so this is a delayed copy of the same transmitted signal, and we keep in mind that we know what exactly is being transmitted. From there I can figure out what is the delta t. Okay, so delta t gives me the time offset in between the satellite and my receiver. Okay, so if you know this delta t, the delta t multiplied by the speed of light is going to give me the distance, or it can also give me the what is the clock offset in between these two devices, right? So if it is t is equal to 1.5 here, at the same time what is going to be the time in this place, because I know the signal took delta t amount of time to fly. Okay, so when the signal reaches here, it ideally should be 1.5 plus delta t, right? So in that way you can also synchronize the clock of the receiver with respect to the transmitter's clock, right? In this case the satellite's clock. Okay, so in a real world, right, how things work is the your clocks that you are using in these GPS devices, they are not like very expensive ones, right? They will have some clock drifts, they are not perfectly going to always be time synced, right? Unless or until you take some special precautions about it, whereas the satellite clocks are all time synced. Okay, so the dot that we have discussed, right, like when you are trying to communicate from a satellite to a receiver, that has to be aligned in some case, whereas all the satellite clocks are time synced. So this you have to remember, all the satellites are synchronized with respect to time, and they are using atomic clocks, right? We cannot afford an atomic clock in a smartphone. Okay, so we have to do something more intelligent about engineering a system such that my smartphone could be synchronized with the GPS clock, but of course I cannot afford to have an atomic clock there. Okay, so satellites do have that. Okay, and that is the reason the satellites will not exhibit clock drift. With time, it's not that their synchronization is going to go away, right, very easily, right? If that goes away, we'll have a serious problem. Okay, but start from an assumption is that whatever is the concept of time that is globally unique or globally same across all the satellites, all satellite clocks, they will have the same time reference. Okay. So, the reference with respect to time they are going to make will be the exactly the same, and the devices are not. Okay. So, we have to come up with a way to do that. Okay. And what is this row 1, row 2 and row 3? These are the distances or the ranges that we have calculated from a given satellite to a to the device. Okay. So, if it is satellite number 1, this is satellite number 2 and this is satellite number 3. So, delta T1 multiplied by C. So, this is could be delta T1. This is the time taken by the signal for traveling from satellite 1 to the device. So, delta T1 multiplied by C gives me row 1, delta T2 multiplied by C gives me row 2, delta T3 multiplied by C gives me row 3. The last one is row 2. Okay. So, we have these 3 ranges, right, and these 3 ranges might not always be perfect, because the our device is continuously uh, drifting, right, the clock they are drifting. So, delta T1, delta T2 and delta T3 might not be directly comparable. Okay. And please note why it is so important, right, why it is so important to use or use this time term, right, in a very precise manner, because it actually impacts the accuracy of the system. Okay. So, because we are multiplying it by the speed of light, which is basically a big number, right, this is speed of light. Okay. So, we know that in one, even if you make a mistake of 1 nanosecond, right, so 1 nanosecond drift, right, in 1 nanosecond light is going to travel 1 feet. Okay. So, if you make a mistake of a few hundred nanosecond, right, which is even a very small quantity, but still, even if you, then you will directly introduce an error of hundreds of feet, right. So, which is basically many meters. So, we cannot directly use these 3 ranges and figure out the location of the GPS device. Okay. Because if you knew because our coordinate reference frame is defined, let us say you know the location of the GPS devices or the GPS satellites 1, 2 and 3, and you know row 1, row 2 and row 3, right. Just using this information, it might be possible to figure out the location of the device, but it will be very erroneous, because delta T1, delta 2, delta T2 and delta T3 are going to be erroneous because of clock drifts. Okay. So, what we need to add? We need to add some kind of a clock drift variable. Okay. So, what is row 1? Row 1 is the range from the device to the satellite, and let us say the satellite is located at x1, y1 and z1 in this coordinate space. Okay. Whatever be the coordinate, like the space be, I am just expressing that in terms of an Euclidean coordinate system where x1, y1 and z1 is the location of the satellite in a 3D space, and xu, yu and zu are the location of the unknown device, like is the location of the unknown device. Okay. So, unknown device in the sense the device does not know its location, unknown location. Okay. So, xu, yu, zu, if we just take the Euclidean distance in between them, so root over of summation of xi, yi and zi minus xu, yu, zu square, that is going to give me the Euclidean distance, and then we are going to adjust the clock drift. So, if the clock has drifted by some nanoseconds or some microseconds, whatever be it, right. So, there is an unknown clock drift also, and that multiplied by C is going to give me some kind of a range offset. Okay. So, this is a corrective measure, right. So, we are trying to put some corrective measure on the range that we are calculating. Okay. Just based on the just alignment of the gold code with the received signal, we have found out some delta t, but we also assume that the delta t has some problem. So, we are trying to correct that. Okay. And for correcting that, we are actually putting this correction measure. Okay. So, we are putting this correction measure, and please note that we are multiplying this clock offset by speed of light c. Okay. So, this part is distance, this part is also distance. So, we can do the same thing for all the satellites now. Like let us say we are having 4 satellites, we are going to come to that point, why do you need 4? We can have this system of equations. Now, what are the unknowns here? The unknowns is the location of the GPS device or the person carrying the smartphone, which is XU, YU and ZU. X1, Y1, Z1 or XI, YI, ZI is basically the location of the ith satellite. Okay. So, Xi, Yi and Zi, these are basically the location of the ith satellite. Okay. And we have this clock drift measure that is used for the range correction. Okay. So, now how many unknowns do we have in these equations? We have XU, YU and ZU, these are the unknowns, and apart from that this is also unknown, because this is not very predictable, right, how your system is continuously drifting, because your system is not supposed to drift, right, because of hardware issues or the temperature that is continuously varying, right. So, some of these oscillators are going to perform very much non-linearly, and that is going to introduce some kind of a clock drift in your system, right, that is really not under our control. Okay. And the only way is to figure that out, right, in a different way. If you can know that what was the drift that happened, we can do a particular correction, but we cannot stop the clocks from getting drifted. Okay. So, now you have 3 unknowns here and 1 unknown here. So, basically you have 4 unknowns, and that is the reason we are going to need the 4th satellite. Okay, because we have to now solve for XU, YU and ZU along with delta clock. Okay. So, only if we know this delta clock, we can figure out precise values of rho 1, rho 2, rho 3 and rho 4, and from that I can easily solve this XU, YU and ZU. Okay. So, I am hoping these systems of equations, right, this is clear, and we call them range equations. Okay. So, we call them range equations, and these range equations we need to solve in order to solve for the in order to obtain or estimate the location of the device. Okay. So, this concept is very generic, right, this does not just apply for GPS, but these range equations could be applied for other kind of technologies like Wi-Fi localization. As I told you, in that case, if I know the location of the access point, right, in case of the satellite it is just going to be the location of the access point, and if you know some kind of a range in between the access point and your device, then you can have this system of equations written up, right. So, the technology that they use, right, it is not based on this gold code, that will be using some different technology, right, but the mathematics, right, that once you obtain some kind of a range, how do you basically solve this equation, that is very similar. Okay. So, just keep that in mind, we are going to refer back to these range equations again and again. Okay. So, we have to solve it, right, and one of the common approach that we follow is basically linearization. We can always solve this optimization problem by using a least square optimization, or any other convex optimization methods can be employed, right. So, one of the, and I am going to also go through them in the next few sessions, right, so that you have a good coverage of solving such equations, right. So, today I am going to show an approach where I just reduce this into linear terms, right, and then solve this. Okay. So, we have to keep a few terminologies before actually trying to solve that actual equation. So, rho I is the current range estimate, and rho I hat is basically my previous range estimate. Okay. So, what was my previous range estimate that just happened in previously before obtaining rho I, and rho, and so the XU is basically your XU hat plus delta XU, and similarly for all other dimensions, right. So, YU is basically YU hat. So, the previous estimate that you have measured, plus delta yu. So, this is the shifts that you have in the x, y and z direction, okay, shift of so this is a shift and this is also a shift. So, these are the delta terms that is added to your previous estimate to get the current location. Okay. So, this is just some of the terminologies that we are going to define, okay, and rho I is basically the range. Okay. So, xi minus xu, this is actually the analytical form of the range, right. So, there is this is the actual true range, this is not based on estimation. Okay. So, xi, yi and zi is the true location of the satellite, xu, yu and zu is the true location of the device. If you just find out the Euclidean distance, you get the range. Okay. So, this is the actual range and the rho i's are the measurements, okay, that of course has the c multiplied by the tu term for the offset or the range correction. Okay. So, now what we do is that we take such equations, right, and we start using the Taylor's theorem in order to linearize this set of equations. And I am just everybody you have covered Taylor's equation, Taylor series and Taylor's theorem, right. So, I am just going to give a small introduction to that, like a short introduction to what Taylor's theorem states. So, if you want to expand this term xt, right, where t is your argument of the function x, right. So, you can do it in terms of x0 plus x dot, which is basically your first order differential. Okay. This is the first order differential. Okay. X dot of t0 multiplied by t minus t naught or t0 plus half of x double dot. So, this is the second order differential, again multiplied by t minus t naught whole square plus dot dot dot, you will basically get the higher order terms here. Okay. So, x triple dot t0, t minus t naught whole cube and so on. Okay. So, like many other applications, right, if you want to linearize it because of the magnitude of the values of the higher order terms, we often tend to ignore them. Okay. So, there could be quadratic terms, there could be cubic terms and we are going to ignore them. Okay. So, we are just going to ignore them and we are just going to use the terms that are linear. Okay. So, these are the linear terms and we are going to use them for our expanding the range equations. Okay. So, and you can just simply put the values and see that the higher order terms are like actually small enough to be neglected, and I want you to actually think about it and why, how small it becomes with respect to the rest of the linear portion of the terms, right. In that way you can actually appreciate that why these terms could be ignored very safely. Okay. Because the kind of accuracy that we are looking for could be achieved just using the linear terms. Okay. So, just keep this in mind that we are going to use expand xt as x of t naught plus x dot of t naught multiplied by t minus t naught. Okay. So, that is the takeaway from the Taylor's theorem which we will be using for linearizing our equations. Okay. So, now if we have three variables, of course, we just not have a single variable t, but we will have xi, yi and zi, and you might even have four terms where you have a time, right. So, ti might also be there. So, xi, how you express xi is basically xi naught plus delta x. Okay. So, delta x I naught basically. Okay. What was the delta that was produced from the previous range or previous location xi0, okay, or xi naught. So, same for x, y and z, we have this delta terms, right, delta x, delta y and delta z, right. So, these are the terms that are going to be subtracted, right. If you see, we use t naught and then t minus t naught, right. So, this t naught in this case are going to be the first portion, right, x I naught, y I naught and z I naught. So, this basically becomes this. Okay. So, f is the function and we are using x I, y I and z I. This is equivalent to, I have just expanded them because we have the notion of the previous range estimate and the current range estimate, and there was this difference of delta x in the shift that I just spoke of now. Okay. And for this x I naught, y I naught, z I naught, this is the x of t naught plus, then you basically do a differential with respect to x, y and z, because you have these three variables now, we have to have these partial differentials, that is all representing the second term, right. This entire thing represents the second term. Okay. And this is your second term, x dot of t naught multiplied by t minus t naught. So, in our case t minus t naught is basically the delta terms, right, delta x I naught, delta y I naught and delta z I naught, and this is ddx of this function. Okay. So, this will be a partial derivative. Okay. So, we are now more prepared to actually expand our equation, and let us see how it looks like, right. So, just recollect whatever we had in the very beginning. We had the current range estimate, we have the previous range estimate, and we have the true value of the range. Okay. So, this R I cap is basically the true value of the range. Okay. So, now if you simply use the expansion that I have shown you earlier, right. So, delta f delta x, right. So, this was this f of x, y and z, right. So, if you expand one of these terms, right, you can just do it as an exercise, right. So, what is your function? This is your function. Okay. And you are simply taking a first order differential. Okay. So, what you will end up in is basically x I minus x hat of u, this is the unknown, divided by r I. This is basically coming from the fact that you have this in the denominator. So, you have this long expression in the denominator, this long expression in the denominator that you are basically replacing by the r I cap, right. So, you can do this simple exercise and see. Okay. And we have the um, shifts here, right. So, the shifts we are calling as delta x u, delta y u, delta z u. These are the previous estimates, these are the shifts, right, and this is the current location of the device, okay, as well as the timing. Okay. So, this is there, the entire thing plus c of tu. Okay. So, this is for the timing advance. Okay. So, I will request you to try doing this derivation on your own, so that you also get a feel of these equations, right. So, this is just a simple differentiation that you have to do on this function, and you have to do this partial derivative with respect to x, y and z. I would like all of you to do this one, so that you get familiar with this equation, okay, and try to do some simple manipulation of this equation. Okay. So, once you have that, you have this simple equation, right, which looks much more cleaner than previous, right. So, we have this rho I, we have this rho I hat, and everything here is sort of we know what these things mean. Okay. So, now what we do is simply give names to each one of these terms to ease our computation. Okay. So, we can take this rho I and subtract this rho I cap, which basically means the delta rho I. Okay. What was the increment or decrement in the range? Okay. Because the range could be, I am going far away from the satellite, it could be increasing slowly, or it could be also decreasing. Just take this delta rho I. Xi minus x hat by Ri hat, this is basically termed as alpha xi. Similarly, we have alpha yi and alpha zi. Okay. So, this entire equation now could be written as a function of alpha xi, alpha yi and alpha zi, where I, you have to remember, I is the index of the satellite. Okay. So I is basically the index of the satellite. So for every satellite, we will have this equation written up. Okay. And what is invariant across all these equations? What is the thing that we are trying to solve for? We are trying to solve for this XU, YU, and ZU and TU. Okay. So you can simply have a system of linear equations now. Now you can see this entire system is linear. Okay, it is no longer it does not have any nonlinear terms that we have seen before, right? After applying the Taylor's theorem and trying to and extracting the first two terms, we have removed all the nonlinearities, and now we have a system of equations where every equation is corresponding to some satellite. Okay, so rho I, delta rho I is basically, let us say it is rho 1, distance from satellite 1 to your GPS device, and increment of that. So we are just using delta rho I. Okay. So simply put this in your familiar form, right? So you have this Ax is equal to B form, where you have this metric setup, and on the left hand side we have this delta rho 1, rho 2, rho 3, rho 4. We have this alpha xi grid, right? So this is your all this alpha xi's, and we are trying to solve for the shifts, right? So this is basically just following a simple linearization, we could actually start solving the location of the GPS device. Okay. So some basic things that you also have to know, right, apart from just the equations, right? The equations, you can actually revisit this equation to understand that how these small steps, right, making the linearization work correctly, and then just getting rid of the nonlinear terms, and then solving this system of linear equations, we are able to solve the for the location of the GPS device. We are solving this equation. Okay. So some extra pointers that you also have to know about this technology is like what frequency they are operating in, 1.5 gigahertz band. Okay. So the satellites are actually using a certain portion of the frequency spectrum, okay, that you have to know. And the GPS continuously sends a PRN sequence, a special sequence, right? And that sequence is repeated every 1 millisecond. So that is the predetermined coded signal that I was referring to, and that has a certain data rate. It has basically being sent as 1023 million chips per second. Okay. So every satellite uses a different PRN sequence, and this PRN sequence could be used to identify the satellite. Okay. So and because it uses CDMA, code division multiple access, code division multiplexing, they could be simultaneously transmitting, and since each one of them are using a different code, we could be easily extracting them, we could be able to identify the different satellites altogether. Okay. So apart from just location, you can also find out other information from the GPS data, like you can also sync up your time, because that is a bonus that you are getting from the GPS synchronization. Not only just location, your time could be also synced up. So the GPS time is going to be much more precise compared to your local system time, right? So time could be synced up, you get latitude, you get longitude, and at the same time you can also get an altitude because it's being solved in 3D. You can also get information about your heading, okay, or velocity, okay, which direction you are heading towards, or what is the velocity. So this kind of information can also be calculated by these GPS chips. Okay. So that is primarily regarding the technique, how GPS is going to calculate your location from the GPS signals, right? Your GPS receiver is going to calculate your location from the GPS signals. What is the maths that goes under the hood, right? And we will see frequent use of such techniques in some of the other technologies that we are going to see next, right? But that will give you a sort of a good introduction to how you should think about localizing devices with respect to fixed reference anchors. And in India we have this NAVIC system, right? NAVIC means a seller, right? So based on that pronunciation, right, we often call it a NAVIC system, where we have this Indian regional navigation satellite system, right? We do not have as many satellites as the GPS system has, right? So the GPS system will have lot more number of satellites, but there are, every country has their own, like not every country, but like many countries apart from the US has their own satellite system. Sometimes they are not going to give a global coverage, but maybe regional coverage in that particular country. Like Japan could have something of their own, China has something of their own, India also has this satellite system. And as you can see on the first one, there is a partial failure because these atomic clocks have failed, right? Even if everything is functional, just if the clock fails, right, it does not help us in doing the localization anymore, because that particular satellite is out of sync with respect to the rest of the satellites. Okay, so other than some broadcast message service, it cannot be used for localization. Okay, so this is, you can like look up the more recent information in Wikipedia. They also have some updates about what are the different satellites, when were they launched and so on. Okay, so with this, right, I'll give you a self assessment exercise, right, where you want to download an application, right? If you, all of you will have an access to a smartphone, right, an Android smartphone, let's say. So you can download this GNSS logger app. Okay, so what does this logger app do? It is going to record a lot of GPS internal information that you can do some analytics on, right? And this kind of analytics is going to have a, like, help you have a better understanding of how what is the performance, particularly with respect to the performance, okay, of GPS receivers. Okay, and this performance I am basically pointing towards the accuracy of the location. Okay, you can simply download this app, and they will have a lot of instruction about how exactly you set it up, right? You have to get rid of the uh, uh, like IMU sensors, right? You don't want any location fusion. So we want to turn these things off, because if we integrate inertial sensors along with the GPS data, you will get much correct version of your location coordinates, right? What we need is like a pure GPS, right? We don't want anything other than GPS to get those readings. Okay, so you can play with this particular app and get a little bit familiar with the UI. So they have a very nice explanation in the UI itself what each and every option means, right? And once you get that, I have written up an assignment, right, that you are going to try out. So as I told you, right, like GPS, you might have different countries having their own system of satellites. Like Russia has this GLONASS system, Beidou is a system from China, Galileo is from the European Union, whereas NAVIC is from the Indian side. Okay, so your smartphone might have the capabilities to pick up not just one but multiple of such satellites. It might not just pick up the American GPS system, but also it might pick up this Beidou system or Galileo system satellites. Okay, so we can just concentrate on GPS, right, which is probably inherently available in all the GPS receivers. So we can just concentrate on GPS. Okay, and you can simply take this application and try to see that what are the different options that we want to use here, right? So for example, this network location, right, this could be switched off, right? We don't want any network to tell us the location, right? So this could be based on your cell ID. Okay, we don't want a fused location, right? We don't want that, right? Because it can use your IMU sensor data and correct your GPS locations. Okay, so navigation messages we might need, GNSS status we might need, measurements we of course need, right? And that are going to be logged, right? So you can simply log this data. Okay, So I have described how you want to do this entire exercise, and I'm going to share the PDF with all our candidates here. So I'm going to email that a copy of the PDF, so that you can, like, all the links are there, you can try it on your own. Okay, and once you have installed this application and you have gotten familiar with the different controls, you have started logging your GPS coordinate successfully along with the control data. So you'll actually, apart from the GPS position, okay, you will have access to a lot of control information. Okay, and we want to analyze such control information and try to see that how this different information correlates to the accuracy of the GPS location. Okay, so uh, how much is the noise in the position, how much is the variance in the position information, and how it is related to control information. And control information could simply mean how many satellites are visible, or what is the signal strength or the SNR of the signal that I am receiving from a particular satellite, right. So those are the information we would really like to correlate with the accuracy of the GPS position, and that is going to give you a lot of insights into why a GPS system is failing for some reason, or in a, like, suppose you have put a GPS chip in a on an IoT device, and this IoT device in a particular environment, right, and you see a lot of erroneous positions, right. You should be in a position to debug such problems. Okay, that is the expectation, or that is the intention of such an assignment. Okay, so and these are the control information that you will get apart from the location. So if you say if you see this sample set of things that you are going to get here, so the red lines are something that are of importance in this particular exercise, but you are free to explore more, right. Apart from latitude longitude, you can also have the speed or accuracy, right, the accuracy. So the system also thinks that there is a certain accuracy of the latitude and longitude. Okay, so what is the time, right, what is the bearing, and also these kind of things you can also look at. Okay, but for this one we are going to primarily concentrate on the latitude and the longitude values and provider, right. So provider is your GPS. Okay, that is what you have to remember, right. It is, if it is something else, right, we are in this exercise we are not looking at Navic, or we are not looking at GLONASS or other systems. We are primarily looking at GPS. Okay, and there are some status lines. So these are fixed lines, it's known as fixed lines, where we receive GPS fixes, and GPS fix is basically once the location is updated, it is known as a GPS fix. And then we also have a status line. Okay, so in this status line we can have lots of different control information, and some of the things that I have highlighted are could be that could be used. Okay, so constellation type. Okay, the constellation type I have said only use GPS. Okay, so you can see other flags, but you can ignore them. Okay, and this directly goes to the Android GNSS APIs, right. If you look at this Android GNSS APIs, you can figure out if the flag is 2, what does it mean, if the flag is 3, what does it mean, and so on. Okay, so the first one is the constellation type. Make sure that you select one of them, otherwise if you mix up the data it won't make much sense. Okay, so then there is a satellite ID. Okay, followed by the signal strength or the SNR received from the particular satellite. Okay, so this is the CB0 dB per hertz, right. So you can use this as a proxy of the signal strength. Okay, so this one, how strong is the signal from the satellite to the device. Of course, if you have a building in between, right, let's say your satellite is here. Okay, and this is your receiver device, and you have a very tall building that is obstructing this line of sight from a particular satellite. You are receiving a feeble signal. I mean, the signal could also arrive because of reflections from multiple surfaces. Okay, but this is the direct line of sight, as it is known as LOS, right, that is blocked by a building. Okay, so this is a building. Okay. So, in such cases what might happen is the SNR could be poor, the SNR may be poor in such cases. Okay. And often the SNR could be so poor that you are not even able to locate, or you are not even able to receive any messages from that particular satellite. Suppose instead of one building you have like a series of many buildings, and your GPS signal from that particular satellite is completely cut off. Okay. So, in that case you will not even receive or hear from that particular SVID. Okay. So, that SVID is basically as a missing. And then there are two other things. There is this azimuth degrees, is basically which direction. Suppose I am taking a bird's eye view of the place where you are standing, right. So, you can either look at, let us say, north, you can look at the east direction, right, you can look at the west direction or the south direction, right. So, which direction you are actually heading or looking at, right. So, that is basically your azimuth. And you can think of the 3D, and in 3D because you can also have your on the top side, right, if you take a 90-degree angle, right, vertical from that plane, okay, whatever we refer as the zenith 90-degree. Okay. So, you can also calculate your elevation, right, how much, like it is, think of how much you need to raise your head in order to view the satellite. The satellite is in a particular direction, right. So, that direction is given by the this azimuth, right, direction of the satellite, because if you look towards the this northeast kind of direction, you will be able to see the satellite. But now the satellite is not in the same plane as the ground, right, you have to raise your head, right, what is the elevation of the particular satellite's position. So, that will be given by the elevation from 0 to 90-degree, because straight is like it is in the horizon, right. So, 0-degree is like horizon, okay, and 90-degree is like above your head, it will be some value from 0 to 90-degree. Okay. So, this information is also available. So, now think about it, if the elevation is like very less, right, let us say 10 degrees, and you have a lot of buildings in front of you, of course your SNR is going to go down. Okay. So, whenever you are receiving a fix, you need to basically see that whether this particular status line was used in a fix, and then try to correlate the accuracy of that particular fix with such control parameters. Okay. So, used in fix is the most important thing here, because you have to kind of understand that whether this status line was actually used in a certain fix or not, because you might be get such status lines and some of the status lines would be simply ignored, right. You might have like 8-9 status lines and all of them might not have been used for a fix. Okay. So, use only those that were used for a GPS fix. Okay. So, I hope this is clear, right. And then there are other control information that you can simply look up in this Android GNSS APIs to understand what they mean. Okay. But these are primarily sort of very important ones, whatever I have highlighted, and you can simply get an idea by playing with this data. Okay. So, I would request you to collect a lot of data. Okay. So, as I have mentioned later, you can actually collect this data in several situations, right. So, I have told you to collect this data in under the open sky. So, that is one case. So, open sky where all the GPS satellites should ideally be visible, right. And then you can come a little bit towards your entrance of your home, right. You can either go to a window or a door, right, where the sky is partially visible. One idea could be that one side you can have the sky visible and the other side is completely blocked by your room environment. Okay. So, it is kind of partially visible. And then the third case is where your sky is completely not visible, or a very limited portion of the sky is visible because your device is deep indoors. Okay. So you are completely inside the building or completely inside your room, maybe from a little small porch or like a small window that could be visible from far, right? From that part only you would be able to see the sky, right? Because if the completely the GPS signal is cut off, you can't do anything, right? There will be no GPS fix at all, right? But I'm trying to deliberately make the reception quality very poor, right? And on the first case, case number 1 or case number A, I have the reception quality very good, right? And you need to make sure that it's kind of bright. If it is very cloudy, right? So in those cases, GPS signals might have issues, right? So make sure that it's a sunny, bright day. You can receive the GPS signals with ease. Okay, and collect data corresponding to such use cases, right? Such scenarios. Okay, so once you have done that, one idea would be start comparing them. Okay, so because you do not have access to the absolute ground truth, right? You do not know what exactly the location of the device is, right? Because GPS is going to tell you a number, right? And you definitely cannot believe that, because indoors it will be very, very erroneous. So one proxy, instead of using a proper ground truth, what we are doing here is you can simply take an average. Okay, you can simply take an average of all the data points that you have for a given location. Suppose you have collected 500 GPS fixes, right? And you can take an average of those 500 GPS fixes and use it as a ground truth location, and then try to see how much each individual location fix varies with respect to that, and that is what we can call an error. Okay, so as you see that if you go more towards inside the building, right, you will have higher and higher errors. So whatever I have plotted here is a CDF, right, and I want you to repeat this exercise by collecting your own data, right? So CDF gives you how much is the spread of the data and what kind of distribution does the data have, right? So if you see in case of indoors, there could be a lot of variance. Okay, so with respect to whatever ground truth we have assumed, the data keeps on fluctuating, right? And why? You can think that it could be because of the poorer SNR of the signals or not lack of visibility of the satellites. The satellites might not be visible. Okay, so similarly you can try to plot the number of satellites that you are able to see, right? So often indoors you can only see at most 4 satellites, right? 1, 2, 3 or 4, not more than that. Whereas outdoors there could be cases where you can actually see 9 or 10 satellites. Okay, so you can do such an exercise and try to appreciate that how the number of satellites that your device is able to see correlates to the location error, right? So there are some questions I have asked, right? How does the distance error for a fix correlate to the number of satellites used for that fix? Okay, so because you will know all the different SVIDs that were actually used for a certain fix, and you can count them. Okay, and in that way you would be able to correlate the distance error. Similarly, not only just the fact that you could see a satellite, but also what was their average SNR. Okay, what was this CNZ dB per hertz entry for that particular satellite. So you have to also look at the average SNR for that particular entry and see how this average SNR bit is going to correlate with the location fix error. Okay, so you can repeat this for all the 3 data sets that you have collected: outside, partially outside, partially inside, and completely inside the room. Okay, and try to observe what is going on. So some samples I have given you, right? So what is the error and the number of satellites? So if you see the number of satellites is quite high, the errors also decreases, whereas sort of here the error is on the higher range, but the number of satellites that you are getting here is also very low, right? So there could be many reasons, not just the number of satellites, but also the position of the satellites, what is the azimuth, what is the elevation, those things, the geometrical properties of that particular orientation also matter, right? So that is going to be discussed in some time later, right? So just to give you an intuition that Suppose you are standing here and on left hand side you have this open sky, whereas on the right hand side you have this entire series of buildings, right. So which means that all the satellites which are on your right hand side, right, are going to be cut off. Although you can see a lot of satellites on the left hand side, but this is going to constrain the geometry of the localization process, right. So in that way you might see higher error compared to if both of the sides were sort of open. You could have also received some satellites from the right hand side and some satellites from the left hand side. That will give you a better accuracy, right. We are going to discuss these concepts in the next class, but at least you can start appreciating these facts, okay. And again on the right hand side I show a plot of the error versus SNR. This is also something that you can try out, that if the SNR is less, whether does it really mean that is your accuracy is going to go up, okay. um, there is one more thing, this is the azimuth, right. So as you are seeing here, so some of the direction where in the direction of the open sky, that will have a very high SNR, right, because as I told you, azimuth is in which direction your satellite is. Suppose it is your house and you are seeing that the strongest satellite with the highest SNR is in this direction. So it could be, you can actually correlate that in Google Maps, right. So suppose your phone was kept here and you see the satellite that has the highest signal strength or the highest SNR to be in this direction, okay. So you can simply see that in this particular plot, at an azimuth of 80 degrees or let us say 80 to 100 degrees. So there are like two satellites which does have a really high SNR, and that is basically helping me in getting the location fixed in a much better way. Whereas in the other values of the azimuths, the SNR values are kind of low, okay. So these are low values, okay. This is a good higher value, let us say, okay. So this is something that you can analyze for your own data set, okay, and that is going to help you get better insights. Same for the elevation also, okay. So with this I am just going to share you, after the class is over I am going to send out the assignment link, right, that you can download and try it out yourself, okay. And do some of this analytics exercise, right, and if you face problems, please you are feel free to get in touch, right, if you have a problem, right, in order to, if you're not able to solve something, or if the intended exercise is something that doesn't you have suggestions for doing it in a different way, like I'm happy to hear from you, okay. So with this was an introductory session, and then we had the discussion about GPS, right. So I would ask you guys, right, if you have any particular